All right, and welcome to another live stream. This is a Portland State University Learning Center live stream for the Physics 212 with calculus. We're going to get started. Before we get started, actually, I wanted to post a few links that are useful. We have some links to the Learning Center's website, as well as following our Learning Center on Facebook and Instagram. Those are going to be posted into the chat here. Boom. And I'm going to do one more link for an attendance sheet. So if your teacher is asking for extra credit opportunities or anything like that, make sure to fill out this form that's coming up next. Send in the information to let her know that you are here. We are going to get started talking about electric fields a little bit more in depth here. We're going to go over some calculations on electric field, as well as looking at the electric field generated from a uniform like line distribution, arc distribution, rings, planes, and other fun things like that. So we got a lot on our plate. I wanted to start off with a Phet simulation on electric fields. This is a great simulation. If you just search the internet for Phet, they have a lot of really cool physics, chemistry, and other science demonstrations as well. This one specifically will allow you to place your own charges, charged particles everywhere, and it shows you the electric field. So if I drag a positively charged particle out there, it kind of radiates out in all directions, the electric field. And you can move it around a little bit, and the dimness of the vectors on there kind of show you the intensity. So the brighter vectors are going to be more intense electric fields, and it kind of fades as it goes away over distance. So we can move those around and we can kind of see how it works. We can also place another positively charged particle there, and we can see how the fields kind of manipulate with two of them there as well. We can throw a negatively charged particle in there and see that that kind of sucks things up. So the electric field goes towards that negatively charged particle and away from the positive ones. And you can see the field kind of going between them, and it'll actually arc on either side, wrapping around as it gets attracted by that negative charge, moving another positive around. So you can play with this if you go on their website, and you can move things around a little bit. You can even throw a sensor in there, this little yellow dot. This is kind of like a test charge, and it will show you the magnitude and direction of the electric field at any of these points. All right. So the farther away we get from it, the weaker it's going to be. The closer we get to the charge, and notice it's going away from that positive charge, it gets stronger and stronger. As we loop around, it starts moving kind of towards this negative charge here. So we can really have fun playing with this and kind of seeing. You see, like right in this area here, there's no electric. It's like a little eddy of electric field. The electric field is kind of canceled out in all directions in that case. That summation of the different electric fields. It's really a fun tool to play around with. You can move. You can really get an idea. And remember, it's not happening on a plane. This is happening in three-dimensional space. So it's not just happening on that XY plane of the page. It pops out of the page. It dips down into the page, and it's a fully three-dimensional effect. So it's a really cool thing to play around with. They also have one on forces. If I can find it, there it is. And we can look at it at the macro scale. And basically, there's two different charged particles. You see that the blue one there, it has a negative charge. The red one has a positive charge to it. And when we move them closer together, their force vectors kind of show. And it'll actually calculate the force between those two. I'm going to go ahead and turn the calculation off, because really we're just looking at the equal and opposite magnitude and direction is what we're looking for there. And the farther they get away, the smaller those forces become. The closer they are to each other, the bigger those forces become. And we can change the intensity of them, so they're not getting any closer, but now suddenly that negative charge is -9 microcoulombs versus, and we can go both positive, and now we see it's more of a repulsive force. They're pushing away from each other in that regard. And there's these little wooden figurines there kind of holding them together so that they don't go flying off the page with the force and acceleration. But they're really cool simulations to play with. We're going to play around with a few different simulations here today, just so you can get an idea of how the electric field is acting on point charges on different places. These are some of my favorites from Phet here. And they have a whole slew of different ones. I highly recommend going on their website, checking out the different things they have. They're very useful. There's also an iPad app, which is what I'm using here. But we are going to switch now to just looking at some electric fields. Now that we saw the basic idea behind things, we're going to try to identify correct electric fields versus incorrect electric fields, and a few different examples here. So this first example I'm going to look at is A there, and it's got a positive charge, and there's an electric field kind of moving out in all directions around it. And the question we have to ask yourself, is this correct? Does this match the model that we know? And if it's not correct, what's wrong with it is what we want to ask ourselves. In this case, it's a positive charge, which is radiating that electric field outwards in all directions. The magnitude and intensity is going to be the same in all directions. So I'm going to say this one's correct. Here. Okay, everything looks good to me there. There's nothing weird about it. It's not asymmetrical or anything else like that. Moving on to the next one, we're going to have a negative charge that's radiating an electric field outwards in all directions. When we look at this one, do we see anything that looks a little odd? One thing is the positive charge radiates outwards. The negative charge actually radiates inwards towards the center of it. So this one's not going to be correct. So I have to say incorrect. And the reason is the electric field is going the wrong direction. It should be going inwards when really here they have it going outwards. So you got to make sure you have the direction of the electric field. The electric field is a vector, which means it has that direction implied with it. Looking at number C there, we see it's a positive charge and it's radiating out in all directions. So that looks really good, but it's really lopsided. There's a more intense electric field on one side than there is on the other. And that's not right. It's supposed to radiate uniformly in all directions across. So I'm going to say this one is incorrect. And if you guys have any questions about anything and you're watching this live, feel free to throw a question in the chat and I'll get to it and see it when we'll discuss what you have questions on. Moving on, if you look at D has a positive charge with an electric field moving inwards. So we already said that D is supposed to have this positive charge radiating outwards like on A. So we know that this one has to be incorrect because it's going inwards to that positive charge instead of outwards like we had before and what we assumed was correct. So this one's incorrect. The next one is this negative charge down here in E. It's got electric field radiating in all directions going into the center of that charge. And that's correct because the negative field is always pointed inwards towards the center of it. And it's radiating equally and uniformly across the whole thing. So I like that one. I'm going to say that one's correct. Looking at F, this is going to be the last one we look at here. There's two positive charges, and there's all kinds of funky stuff going on with those electric fields. Because when two charges get next to each other, the field lines aren't straight anymore. They start to bend and swerve, especially when they both have the same charge. So both of these fields are going to interfere with each other. And they're going to be pushing away from each other here. So on that regard, it looks pretty good. What I don't like about it is here and here, we have those electric fields crossing, right? So if I have an electric field moving towards it like this, at that point, they should sum up and cancel out, and they should kind of go to nothing and maybe turn upwards if they're at a slight angle or not. These actually cross through and go the opposite direction. So at that intersection point, really, you have no electric field, but they're drawing it with an extending electric field past each other, both on the top and bottom. So I'm going to go ahead and say that's incorrect. And those are the types of things we want to look at when we're evaluating these electric fields and drawing our own electric fields and things. Are they going in the right direction? Are they uniform around the whole thing? Are there multiple charges? We have to worry about a summation of electric fields at any of these points here. And those are just a few really good examples of what we're doing here. The next thing I wanted to look at is some of the uniform distributions. Now these are some really crazy beasts. So you guys are taking physics with calculus, so they don't just give you a point charge and be like, what's the electric field? We're going to give you charged lines. We're going to give you arcs. We're going to give you planes and circles and spheres and all kinds of other fun things. And we have to then use calculus, of all things, one of the best tools around, to determine whether or not this works and what the charge is, electric field and everything. So I'm going to show a few simulations that I've come up with. See, there we go. And this has a diagram of we have a line charge, an infinitely long line charge here, and I have a point right here, and I can actually grab that point here. And we can move it around, and we can see the electric field kind of gets shorter as it gets longer. As it gets closer to that field, the electric fields get bigger, and these are broken up into the components. So you have the X component here and the Y component there. And as we slide around, this is kind of the point that I'm evaluating it at, that DQ. And as we slide it around, we can see kind of those vectors change as we go along. And there's something really cool about this is this has an X component and a Y component, and this Y component is pointing down in the negative. And every point that's above that point is going to have a negative Y vector. But every point below it is going to have a positive Y vector. So at every point here, there's going to be another corresponding point down here that kind of cancels that one out. And you can see the same idea going on with all of these. Here's a plane over here. And as I rotate this around, we can see there's a kind of a negative Y vector here, a negative Z vector there, and a positive X vector there. As I drag this charge around the plane, you can see, well, the Y vector there is going to start to cancel out the Y vector here. Okay, the Z vector there, that's going to get canceled out by the Z vector down here. But the X vector never has anything that cancels it out. So the charge, the electric field at least, is going to only be in the X direction going away from that plane. And this is assuming we have a positively charged plane, of course. If it was a negatively charged plane, all these vectors would be reversed. And this X direction would be going towards the plane as opposed to away from it. But for diagram's sake, I like to use positive charge. You can see it radiating out from it. Moving on to the arc that's down here, we have that same idea. Here I actually drew in these dashed lines here. That's actually the symmetrical charge that's going to counteract in this case, the X vector, where the Y vector is actually going to be summed up and continuous upwards. So at every point here, this point is going to have an X component vector that shoots out in this way. It's going to have a corresponding point opposite to it that's going to cancel out that vector. And the summation of these two red vectors is going to be 0. It always goes down to nothing. And the only thing we're left with is a Y vector going straight up. And we can evaluate this at every angle going in here. So if I call this one 0, I can say it's from negative 90 all the way to positive 90. And you can see on this side, the vector shooting, well, yeah, this way. My camera's reversed. This way. And on the it has a corresponding vector on the other side shooting back the other way just to cancel them out. And we can see the right triangle drawn in there, our radius here, the direction. This is the X component of that radius, the Y component. So just a little trigonometry, and it's all drawn in. It's a good way to visualize kind of what's happening in here. Same idea with this ring. The ring is a fun case because it's three-dimensional. We've got this round ring, and then we have a point floating off center of it, okay, at some distance away from the center. But it's in the center line still. And since it's in that center line, we have this symmetry going on where the X and Y components are going to fluctuate, but ultimately when you get all the way around the ring, it's going to cancel out. If you did the same thing with just a semicircle, like we had on that previous example, just here, notice the Z vector is only negative there, right? So your magnitude of vector in that case would you still have a large X, but you'd have a bit of a Y, or sorry, a bit of a Z going down, but the Y's would cancel each other out. If instead you had a semicircle that started up here and then worked its way all the way down to the bottom, okay, then your Z's would cancel out and you'd have a Y positive. And your vector magnitude direction would kind of go split between these, probably going more towards the X because the X is always going to be added to each other, where the Y is going to fluctuate a little bit more. But those are some cool simulations and ideas so you can visualize kind of what's happening at each of these points and each of these charges going through. And what we're going to do is we're going to evaluate, well, how do I calculate some of these things? And let me flip back to this guy. So we're going to start off with a line. And I'm going to just use this line drawing. We have, of course, breaking this down, we have that right triangle there. We've got the hypotenuse there using the Pythagorean theorem is the square root of x squared minus r squared. There should be a plus r squared. I have that wrong. And that's x there. I think it's supposed to be a plus. It just can't see it. It's broken up the text a little bit. And then I have r here. This is kind of the distance we are away from that. Think of that as L, the length of the line. And if your line is infinitely long, this is going to just sum up to that straight line there. And we can actually evaluate it from some distance above and some distance below. And if we have that line right in the middle, the below will cancel out with the above equally. And we'll end up with that's just x component, basically. So let's look at how would we calculate that. All right, so here's kind of, I have that diagram of that simulation, and you can see it's a plus there. And we want to calculate the magnitude and direction of the electric field at 2.2 meters from a long wire. So this distance x here, this is equal to 2.2 meters. Okay. I like to pull information out of the problems as I see them. And when it says it's a long wire, right, I'm going to assume that's an infinitely long wire, right? So it goes on forever and ever and ever for the most part. And we're just going to call that length right there kind of L for now. Let me switch. All right, and then what we have, and that long wire is uniformly charged with a linear charge density of 3.8 times 10 to the negative 6 coulombs. So that's microcoulombs per meter. So what we need to do is use the electric field equation that's above me, where it's the force divided by that charge, or K, which is equal to 1 over 4 pi epsilon naught. It's KQ over R squared is the idea. So I want to use this simple idea of KQ over R squared, and I want to generate a formula which I can use to solve this. Now, since we have symmetry in there, well, let's look at just one point. At any one point on here, I can't move that one. At any one point, we're going to have a force going along this radius that's here, along this radius here, right? And that's going to be our distance, that R squared. So we know that R is equal to the square root x squared plus R squared, right? And I got a capital R in there because that capital R, in this case, I'll call it R squared. That's this distance here. And Q, well, Q is defined here, right? But that's the charge of the entire line, right? So we can't just write Q. We have to kind of write it as Q over L. Q over L, which is the charge per distance, right? And they told us that charge density is what that is equal, we're going to call it lambda, which is equal to 3.8 times 10 to the negative 6 coulombs per meter. So that gives us the lambda distance on there, and we know that x is equal to 2.2 meters. So now we can kind of start to formulate out this idea, and I can leave in k is equal to 1 over 4 pi epsilon naught, which is approximately 8.998 times 10 to the 9th, and its units are newtons meters squared over coulomb squared. So when we derive this into our formula now, one thing I'm missing, I guess, is I got R up there. Good. Okay, I know that the electric field in the x direction is going to equal this value we have times, and then if this here is theta, or angle, this is going to be times cosine theta. And it's cosine because we're looking at the vector going adjacent to that angle that's there. So now we can kind of start to derive this equation. And what we want to do is we have to replace this idea of the charge, big eraser, small eraser, with the change in force over the change in time, right? So I can write it as dq over L dx. I'm going to make that go over a little bit. So it's dq over dl dx. So as it's that charge density, that instantaneous charge density over a small instantaneous section of charge, and we're going to integrate as we go along those. And we can integrate that whole thing. So I'm going to write it below. E to the x is equal to the integral. I can do it from, say, negative L to positive L, or the length entirely divided by 2. But really, we know since there's symmetry on there, we can just double it from 0 to L over 2. Right? So that's what we're going to do. I'm going to start at 0, go to L over 2, and I'm going to double this. And it's going to be twice as big. That's K dq over L dx divided by, I'm going to write in my radius that's up here, the square root of, in this case, my, I'm going to go over the entire thing at that point. So I'm going to say it's L over 2 squared plus x squared cosine of theta. And I'm not going to go through all of the kind of derivations in there because there's a good video that your teacher has done on your Cogbooks platform that goes through the derivation of all the calculus. But at the end of the day, okay, we can write calculus scribble. We're going to save time for a couple other problems. Is equal to 4 pi epsilon naught. Okay, and this we have our lambda times L over x, and that's going to be times 1 over square root of x squared plus L squared over 4. And there's one thing, when you have an infinitely long wire, this idea of x becomes infinitely short. The relative distance of x doesn't seem to matter. 2.2 meters is a very small piece of a long, infinitely long line. So x here, we can simply ignore. And that lets us take the square root of that L squared over 4, making it just be L over 2. That 2 is going to pop up to the top, so we're going to end up with 1 over 4 pi epsilon naught. And the L's are actually going to cancel out here and here when it's all done. So times lambda over, and there should be a 2 in there because I left my 2 out here, didn't I? So 2, and then I'll bring in my 2 here. 2 lambda over x. Yeah. Oh, and then k is going to be this value here. So we can simplify it and just write it as k 2 lambda over x. And that's going to just be in the I direction. So that's kind of the formula we can use to solve any of these. And we can now apply that to these variables that we have up here. Because we have a value for k, we have a value for x, we have a value for lambda, which is over here. So now we can just plug and play. We can plug a few problems in. So writing that into our formula, I can say this is 2 times k, which is 9.9 or 8.99. 8.998 times 10 to the 9th. I'm going to leave units out for now because I'm running a little bit short on space. Times our lambda, which is 3.8 times 10 to the negative 6. Those are Coulomb meters. Divide by our value for x, which is 2.2. And if we do that, switch over to my calculator. I'm actually going to write this out as 2 over 4 pi epsilon naught, unit conversions, constants. I have all these constants in this calculator. It's wonderful. And there's epsilon naught. The value is 8.854 times 10 to the negative 12. And the units for that is kind of force meters. And then we're going to multiply that times 3.8 times 10 to the negative 6. I'm actually going to put my units in here. These are coulombs per meter. And we're going to divide that by 2.2 meters. So, and we're going to square that. That's one thing no, I don't need to square that. Square it with the electric field. But that should give us a proper, we have, what is it, 31,047.9 Newton coulombs. That's the strength of the electric field next to an infinitely strong line. It's a really strong field when it comes down to it, but it's a really long line as well, and you're not that far away from it. So that's going to be 31,000, 47.9. So I'll write that here. 31,047.9, and the units for that is going to be newtons per coulomb. And that is the unit for electric field. So we got. So that's the answer for calculating that magnitude and direction. The direction, if we want to put it in here, is just going to be, in my case, the x direction, right? So I call it I hat. So you get that vector notation in there. So next thing I want to tackle on here, if there's no questions or anything on that, is we're going to look at the same idea, but we're going to do that arc now. That arc kind of is a very similar beast to the other thing. Let me switch over to my arc simulation real quick. And I like this one because I actually drew in the canceled vector as well. So you can see that in this case, the x components are all going to cancel out. At every point, there's another vector that cancels out the other side. And that y component is just going to continuously add to itself over and over again. And we can start from here and go all the way around. We have to integrate this whole thing. But if we see this as 0, this is negative 90 over here, and this is positive 90. If we integrated from negative 90 to positive 90, that would work great. But it's always easier if you can see that symmetry in there. And because of that symmetry, I can integrate from 0 to 90, and then just multiply my answer by 2. Seeing that symmetry just makes the math a lot easier, and it makes the physics behind it a whole lot easier to deal with. So that's how we're going to tackle this one. Go back here. My window doesn't want to move. It moved. Good. So we can look at this, and when we see this dq, this is the charge just at that infinitesimally small point, is going to travel over some distance. And this really small distance, kind of between a point right next to it and a point over here, I can call ds. Is the idea. And that ds is just kind of the arc length of that infinitesimally small arc length that's going on in there. And we can find ds by it's r d theta. So I'll write that kind of up here. So ds is equal to r d theta, where theta is the angle kind of going on here between that center line and the arm, which is the point between, or the line between P and dq. So then d theta, we can then oscillate there between 0 and 90 degrees. And then we have kind of this line density that's there as well. We're not actually going to do a lot of the calculations for this. We're just going to derive this formula. This is the one we're going to go through the integration for. So we're going to call lambda, in this case, the linear charge density. And that linear charge density is equal to the change in charge divided by the length, dx. Or in this case, I guess instead of length, we'll call it arc length, s. That ds, right? Yeah, dq over ds. So since that's equal to lambda, we can actually rearrange this a little bit and say that dq is equal to lambda ds. Which, if we substitute in our definition up here, that's equal to lambda r d theta. Now, if we remember, our electric field from one point, right, is equal, that electric field is equal to k dq. In this case, I'll say dE, the change in electric field is equal to dq divided by r squared. Well, that dq we can then substitute in, so that's equal to k, what did I just say, theta r d theta over r squared. And we already have an r in the top and the bottom now, so we're going to cancel those out before we go any further. Simplify our lives going forward. That's just going to be k lambda d theta over r. So now we get to integrate. And we're looking at just, in this case, the y component of it. Again, the y component is going to be the vector that's shooting up this direction here from the angle that we have here. If this is our angle theta, then we can say cosine of theta will give us the component vector shooting up out of the top of that point. In this case, this is going to be what I call the EY vector, the electric field in the y direction, because this is my y-axis there. Should have drawn that probably. My axis here is x and y. So the nice thing about this is when we integrate, and we can see, I'm going to use a nice blue color. I could integrate from 0 to 90, and it's only taking half that semicircle, but I can multiply that by 2, do my k lambda dq over r. Now, since most of this is going to be a constant value, right? So I'm going to move back over to here. Okay, that's 2 times the integral from 0 to 90 degrees of, well, let me backtrack, make some space. I want to pull all my constants out of the integral. But we can do that because we don't have to integrate k. We don't have to integrate lambda. We don't even have to integrate. I think we can integrate everything. Oh, this should be a cosine here. Cosine theta. There you go. We don't have to integrate r either. We just have to integrate cosine d theta. So this integral became a lot simpler all of a sudden. When we stopped integrating from negative 90 to 90, and when we pull out all of the constants, we just have a cosine theta d theta to integrate, which is a pretty easy integral to make. So that's going to be 2k lambda over r, and then that's times the integral of cosine is just sine. So we can just go to sine theta, and we're going to evaluate that from 0 to 90 degrees, which is equal to 2k lambda over r, and then sine of, we're going to multiply this by sine of 90 degrees minus sine of 0. And sine of 0 is 0. Sine of 90 is 1. Makes our life easier. This whole sine difference is just going to be 1. And our value is going to be this. So this can be a formula you can use to kind of plug and play the electric field at the point at the center of a semicircle. And that point's going to shoot, in this case, in the y direction. So I should put this 2k lambda over r j hat. And that direction depends on the angle of your arc, of course. Any questions on anything that I've done so far? If there is, throw them in the chat. I'm happy to answer or help anything out. The next problem I wanted to deal with is this guy here. And this one's a little bit simpler. We're not going to do any crazy integration here, but we are going to look at the electric field and the forces on charged particles. So what we have here is, consider that there is a 1.4 times 10 to the negative 10 meters, or consider an electron that is 1.4 times 10 to the negative 10 meters from an alpha particle. And that alpha particle has a charge of 3.2 times 10 to the negative 19 coulombs. So we want to find the electric field magnitude and then the direction due to the alpha particle at that location, at the location of the electron itself. So if I draw out this diagram. I love to draw diagrams. I have an electron over here. I have an alpha particle here, which is a positive charge. And just looking, what is the direction of the electric field coming from the alpha particle, right? So due to the alpha particle at the location of the electron. So my electric field is going to be the electric field of the alpha particle. And the direction that it's going to be, since it's a positively charged alpha particle, it's going to radiate out from that positive charge. So when that electric field hits this, it's going to be pointing inwards towards the electron or outwards from that alpha particle. So then we can deal with the magnitude of it. And the equation I have above my head tells me everything I need to know. Because that electric field we can calculate as 1 over 4 pi epsilon naught times the charge, in this case the charge of the alpha particle, because we're looking for the electric field of the alpha particle, divided by r squared. And we're looking for the magnitude, so we don't need to worry about the r hat, the direction of it in this case. So let's find the values for this. Well, r is going to be the distance here between these two. From center point to center point is r. And it says up here that it's 1.4 times 10 to the negative 10 meters. So that's about 1.4 angstroms. Exactly. Times 10 to the negative 10 meters. That's my distance in r. My charge, this is going to be q. Q of the alpha particle is equal to 3.2 times 10 to the negative 19 coulombs. So now we can just plug in these values that we have. This whole thing here, we can simplify that as k, which is equal to 8.998 times 10 to the, oh, now my memory lost it. I knew it a second ago. Where's my notes? To the 9th power, I knew that. Newton meters squared over coulomb squared. So now that we have all of those values, we can plug in those, all of those into that equation. We can find that magnitude of the electric field. So that would be 3.2 times 10 to the negative 19 coulombs divided by 1.4 times 10 to the negative 10 meters. I'm going to square that whole thing, including the units. We need to multiply that by this 8.998 times 10 to the 9th power. And this is going to be Newton meter squared over coulomb squared. And notice the notice the units on here. The meter squared here is going to cancel out with the meter squared there. Oh, I crashed. And I back up. Wrong one though. Nope. Here. There it is. The meter square cancels out with the meter square. The coulombs cancels out with just the squared coulombs, leaving a unit behind of newtons over coulomb, which is our unit for the electric field. Now we can go ahead and plug that into our calculator. Going back. So I can say 1 over 4 pi, pull up my lovely constants, epsilon naught, there it is, times, it would be parentheses 3.2 times 10 to the power of negative 19. And those are in coulombs. We're going to divide that by, I'm going to use parentheses because I'm going to have to square this value, times 10 to the power of negative 10. And this is in meters, and we're going to square that whole thing. Boom. Okay, so I have k, which is 1 over 4 pi epsilon naught, times 3.2 times 10 to the negative 19 coulombs, divided by 1.4 times 10 to the negative 10 meters, all squared at the bottom, is equal to 1.467 times 10 to the 11 Newton coulombs. So go back here. So this is equal to 1.467 times 10 to the 11 Newton over Coulomb. And that is the magnitude of the electric field from the alpha particle at the point of the electron. So that doesn't take into account the charge of the electron or anything else like that. We're just evaluating it kind of at that same distance is really all that matters. And you can tell that based on the equation that we used, didn't have the charge of the electron or anything to do with the electron really besides the distance between them. The next step is we want to know what is the electric field due to the electron at the location of the alpha particle. This is the same idea as what we just did. It's backwards now. So the drawing from our same picture, if I grab this guy, I can even do a little copy, because it's the same situation, but now we're looking at it the other way around. So we're looking at the electric field that's from the electron itself. And we can write our same equation, the force in this, or the electric field of, I'll say a little e minus for the electron, is equal to K, Q, the charge of an electron, divided by that R squared. So we can use the same values where R is equal to 1.4 times 10 to the negative 10 meters. And the charge of an electron is going to be equal to 1.6 times 10 to the negative 19 coulombs. And that's just what's one of the fundamental charges of the universe. It's the smallest unit charge, essentially, in there. Everything's going to be a multiple of that. Anything smaller than that, you're going to have to break apart into subatomic quarks and other things like that, which don't usually happen independently, at least not for very long. So we can plug and play all of this equation at this point. Since we have an equation and we've identified the units that we have, it's just the electric field of that is equal to 1 over 4 pi epsilon naught times 1.6 times 10 to the negative 19 coulombs divided by 1.4 times 10 to the negative 10 meters. And that whole value is squared. And that is going to equal out, we can flip back to our trusty calculator. And we can use that same expression we used before, since we can copy and paste. Most calculators, you can go up, select it, and then just change part of it. I'm just going to change this top part up here. And I can actually put in then 1.6 times 10 to the negative 19 coulomb. And it gives me 7.337 times 10 to the 10th Newton coulombs. So that's 7.337 times 10 to the 10th Newton coulombs. Did I write that right? Yep. Okay. And that is then going to be the magnitude of the electric field from the electron at the point of the alpha particle. So you notice if we compare those two, the electric field of the alpha particle is much larger than the electric field. It's about double the size of the electric field of the electron. And that makes sense because the alpha particle is, I think, has about, it says a charge of 3.2. So the charge is about double as well. So it's a proportionality there. The same distance, the only difference in it is that charge. The only thing we change is this charge by about a factor of 2. And our electric field difference is also by about a factor of 2. So we can see the relationship with what happens when we increase the charge. The next question we're going to have on that same topic is what is the magnitude of the electric force on the electron? Well, now we have to use not just the electric field equation, but the force. So the force is equal to, force electric, we'll say, K Q1 Q2 over R squared. Same thing as the electric field, but now we're adding two charged particles. It's an interaction between two particles itself. So I can even say, well, instead of 1 and 2, let's use the electron and the alpha particle there. And we'll say the magnitude of that force, so we don't have to worry about the vector of it. And we can just plug in the same idea and do that whole same equation, putting in the value for R and the Q's that we had. There's a simpler way to do it, though, because we know that if the electric field is equal to the force divided by Q, magnitudes, that would mean that the electric field times Q would equal the force. And if we say that the electric field of the alpha particle times the charge of the electron should equal the force of the alpha particle on the electron. So since we've already calculated this, all we have to do is multiply it by the charge of an electron. So we said that the electric field of an alpha particle, that's the magnitude of that, was 1.467 times 10 to the 11th Newton coulombs. So if we were to just multiply that, do 1.467 times 10 to the 11th Newton coulombs, we multiply that times negative 1.6, and it's negative because it's a negative charge. We're going to take the absolute value of it anyways when we're done, times 10 to the negative 19 coulombs, and absolute value. That will equal the magnitude of the force of the alpha particle on the electron. So I can switch back to my trusty calculator, put in that value that I got for the magnitude of the electric field of the alpha particle on the electron, and I can just multiply that times 1.6 times 10 to the negative 19 coulombs, and it gives me 2.347, let's say 2.348 times 10 to the negative 8 newtons. So that's equal to 2.348 times 10 to the, let's say, negative 8 newtons. So that's going to be the magnitude of the force of the alpha particle on the electron. And what would the direction of the force be, you might ask? Because it is a vector. It's going to have a direction, especially if we draw that free body diagram. Going back, I can paste it in again, I think. It's still loaded. Nope, that's a number. Going back to our diagram here, this is going to have a force on it. I'll make my force color be a nice purple color. So the force of the alpha particle on the electron is going to be an attractive force going this way, because they're different charged particles. The electron's a negative and the alpha particle is a positive, which means they're going to have an attractive force pulling them into each other. So we know, in this case, if we drew our axes, where the positive x is this way, then we're going to have a force in the positive direction. So if we drew that even in, be 2.348 times 10 to the negative 8 newtons, and then be in the I hat direction. Okay, going along that x-axis between, and it's really the axis between the two particles. Delete that. So we can flip the question around. I don't think I put it on here. And we can think, well, what is the magnitude of the electric force on the alpha particle then? Okay, so the magnitude and direction of the electric force on the alpha particle is going to be equal and opposite to the magnitude of the force on the electron, right? Because we're going to have that same force going. So we have that electron here still. We have the alpha particle here, and this is gonna apply a force this way. This one's gonna apply a force this way. And if I was some neutrally charged particle here, put a little n, okay, I'm not attracted to anyone. No one's attracted to me. story of my life. But I would see these two charged particles moving towards each other. They both have an attraction and a force applied on each other going towards. If you were just the electron out here, you would think you're standing still with nothing around it, and that alpha particle would be coming towards you. If you were the alpha particle and there was nothing else around it, you would see just the electron coming towards you. So those forces have to be equal and opposite. In this case, they're an attractive force when they pull together. If they were both positive charged particles, there would be a repulsive force, but it would still be equal and opposite. They'd go in different directions and equal magnitude because both of them apply that same force on each other. So the force of the electron on the alpha particle would then be the same, 2.348 times 10 to the negative 8 newtons. And it'd be a negative, we'll call it, because we'll give it the direction I had. So it's negative because it's going along the negative axis. Even though it's an attractive force, the alpha particle here is moving. Again, if this is my positive x-axis, it's moving towards the negative x-axis. And that's what's going to make it a negative force. It's really, those negatives and positives just imply kind of a direction of the force, direction of that vector that's going on. And that is all that I have for today. If there's any questions or anything like that, feel free to pop them in the chat. You can also drop into our office hours. I'll paste a few links in the chat as well in case anybody showed up a little late. We have links in here for our Learning Center and following the Learning Center on Facebook, Instagram. We also have the Learning Center's website. Those are really useful links if you need more clarification on some of these problems or questions on anything. Drop into the tutoring. You can also make an appointment with me. If you're watching on the Penji website, there should be a schedule an appointment with one of our tutors, either myself or two other great physics tutors here. We're happy to help you out. And there's also an attendance sheet, which is a Google form. I'm going to paste that link next. There we are. So click on that document if you want to get extra credit in your class, assuming your teacher offers extra credit, and make sure to fill it out, and it'll get reported back to them. I hope to see you. I have drop-in hours immediately after this from 1 o'clock to 2 o'clock. So, from 2 o'clock to 3 o'clock. It's almost 2 o'clock now. From 2 o'clock to 3 o'clock, I have drop-in hours. So drop in if you had any questions on what we did or anything else you're dealing about in class. We'll be happy to help you out. Thanks for tuning in, and I'll see you next week.